Okay, hi everybody. Welcome to the second week. So what have you learned so far? We have this equation, EDS minus EDV plus mu dn, okay, so which is some sort of a conservation law for thermodynamics. We know that entropy is a growing function of energy. Okay. What else do we know? We know that if state B is achieved adiabatically from state A, then SD is larger than SA. We also learn how to perform Legendre transformation, right? We can go from E, which is a function of S, V, and N, to any other function phi, okay, by terms of Legendre transformation. So if I call this equation 1, the Legendre transformation allows us to express equation 1 in almost any variables. So for example, we've seen the Gibbs free energy, E minus ds. We've seen the ground canonical potential, E minus ds minus mu n, and we had all different kind of names for these functions, which are basically a form of energy in different coordinates or in different variables. Right? So we call those functions generalized potential. Now, why do we need all this? Well, first of all, because it's some sort of description of thermodynamics that you have learned last year. But it's not enough. Why it's not enough? I need some sort of a principle that tells me what are the right states. This is first. And what or how those states are modified when I perform some sort of an internal modification. Okay? I do something internally. I keep the general or extensive variables constant. I can keep volume constant. I can keep pressure constant. Or the general variables are kept constant, extensive variables. And I do something internally inside the system. And I want to know what happens, right? This is the basic question of thermodynamics. I heat a little bit, I transfer some mass from one place to another, and I ask the question, how the equilibrium state, okay, so just a reminder, all of this applicable to equilibrium states only. Okay, so we are dealing so far, and probably till the end of this class, only with equilibrium states. So I want to know if I started from one equilibrium state, I changed something internally, how the system is going to respond, going to react, going to change, if I'm considering only equilibrium states. So we need some sort of a general principle. This is still not a general principle. Right? This is a conservation of something. What general principles do we know, or have you learned during your physical education so far? Yes? Not in this class. Not in this class. You learn two general principles. One in optics and one in Lagrangian mechanics. Very general principles, yes. Yep. So the minimal action principle, which is the same as the Fermat principle of minimal time, this is a very general mathematical principle, right? So what you have done in the class of analytical mechanics, you started, you said, well, we already know all those Newton equations, but we look for something much more general. And then you proved, right, using Newton equation, that there should be some sort of a minimal action principle. Okay? And then you used it and developed a very general framework for classical mechanics. The same can be done in thermodynamics. Right? Exactly the same. So instead of saying we are starting with some empirical laws that describe of how is my container of gas is expanding when I hit it, right, which was actually discovered like the Newton laws, some specific empirical behavior of the matter. Instead, we're doing something else. We're doing the same thing as it was done in classical mechanics. We will say that there is a very general principle together with some conservation laws, right? And we're going to apply this principle and we can derive all the behavior that people have measured and observed, and it's going to be based only on this very specific or very simple principle, which is similar to the principle of minimal action. And then all the different laws that you studied during your education on thermodynamics can be obtained. So what is this law? So I mentioned two, right? Principle of minimal action. Okay, and I mentioned the Fermat principle, minimal time. So we have some sort of a belief that, observation, that there are quantities in physics that should be maximalized or minimalized in order to describe the proper behavior of our world. Right? The same happens in thermodynamics. Right? In optics, this geometrical optics, it's the time that takes the light to cross from one place to another. In classical mechanics, it's the action. And in thermodynamics, it is entropy. So this is the principle of maximal energy. Entropy. No. It's here. It's actually maximal. Right? Here it's actually maximal. Now, it's an observation. We can prove it based on some specific thermodynamical laws or behaviors, or we can probably start with it and say, well, this is my assumption. This is how I assume that this is what I assume about my world. Right? So how I can maybe think about this assumption, and also the question here is maximal with respect to what? So I need to answer those two questions. Now, let's consider that we have on one axis the energy of our system. The other axis is our extensive variables. And we can plot another axis, let's call it x, okay, which is internal variables. So what I mean by internal variables? Let's assume that I have a box, right? Simple box with gas molecules inside of it. And I assume that this box, or this gas inside this chamber, is in equilibrium. Right? So the extensive variables is the size of the chamber, okay, and I can think about it. There can be some adiabatic constraints or about what happens to the system. internal variable for me is going to be I'm starting to build a wall, right, inside the system. Okay. Okay. Or I can say I have a wall inside the system and I'm drilling holes inside this wall. Okay. So we can think of some internal variable as the length of this wall inside my two-dimensional chamber. So if I want to describe my system, and my system is in equilibrium, if you want to think about some system, let's assume that we have V1 and V2, and it's a gas, etc., etc. So I do know that when all of the system is in equilibrium, and extensive variables are kept constant, there is a specific point in many-dimensional space which describe the position of my system. It has a specific energy, it has a specific values of extensive variables, and I have an equilibrium state. And nothing is changes. What I do, I perform some sort of a modification of the internal variable. Basically, I'm building this wall, or there was a wall, and I'm drilling holes inside the wall. And I know that when I have performed this, the intensive variable have changed, but I'm keeping my energy constant, and I'm keeping my extensive variable also constant. So somehow this state managed to transform into another state. The only difference between, let's call it A, let's call it B, the only difference between those two states is the presence of some internal constraint, right? The presence of the wall, the size of the wall. It's some sort of an internal constraint, not external, but internal. Okay. Now, this is my thought experiment. So in my thought experiment, I'm starting from equilibrium, I'm building a wall, I'm changing from A to B due to the appearance of an internal constraint, right? So I reach this position. Now what will happen, and I'm asking here I have some entropy, SA, right? And here I have some entropy, SP. Now, let's think of the situation that it is possible for me to take this constraint out of the system immediately. And at the same time, keep adiabatic boundary conditions. Okay, so no change of heat happens between my system and the outside world. Okay. What will happen? I have taken this constraint. What will happen to this point that it's now located at point B and has an entropy SB? It will drop down, right? This is what you're suggesting?
Yeah, it will increase from SA to SB. That's what
exactly. So it will go from here to there. Why? Because equilibrium is exactly defined by E and extensive variables. They are not changing. Internal variable disappeared, so I have to go from this point to that point. Now, what is the relation between SB and SA?
SB is bigger than SA.
Who is bigger?
SB.
SB is bigger?
לא יכול לכתוב על מי.
No!
רגע, אבל זה היה מחובר ועשית חורים?
I started from here, I changed my internal constraint, I reached here, and then I have taken it out while adiabatic boundary conditions were concerned.
Can you explain again? You had the מחיצה.
I started here. I had no wall. Okay, I had no wall. I had no wall.
A, no wall?
No wall. No constraint. Okay. No wall. I built a wall. I built a wall.
In a moment?
It doesn't really matter how. Okay.
But
Magically. B is wall?
Let's as you wish. I build a wall. I build a wall. But I build a wall such that my extensive variables were kept constant and the total energy of the system was kept constant. How much time it have taken me, I don't know.
you can do it adiabatic.
I don't want to do it adiabatic. Otherwise, I cannot do it basically. And I will show you why.
That's why I'm asking.
Right. So if I have built this adiabatically, then SB is larger than SA. But I can do it not adiabatically. Okay? So let's. This is why I introduced the adiabatic boundary conditions only at the moment when I'm removing the constraint. Okay? I don't care how I reach this situation, as long as I conserve energy and extensive variables. But the point of this argument here is that when I'm reversing the situation, I want to reverse it adiabatically. I don't care how I reach this point, but I'm going backwards adiabatically. Okay. What? Yes?
But if you said you can't do it adiabatically, how can I?
Well, I can. It's meaning that I'm producing work and some sort of heat has to enter into the equation,
so
right?
How can I conserve energy?
T ds or T ds. This is dq, right?
Yes.
Okay, plus mechanical energy. Mechanical energy. Energy equals dE. So if this is 0, and I'm performing some mechanical energy, there has to be some sort of a heat. Okay?
So we're assuming we're conserving energy.
I'm saying, well, I'm capable of doing this. Okay. At least in my head. Okay? So what happens when I remove it instantaneously?
B's wall.
B's wall, yes. Yes, it is. B's wall. What happens? Who is bigger?
SA.
SA is bigger, right. SA is bigger than SB. Okay, and in order to take into your account your concern about maybe I build this position adiabatically, you can say that it's bigger or equal.
May I ask a question?
Yes.
I don't understand. Wait, from SA to SB, what did you do exactly?
I built a wall.
Built a wall adiabatic.
No, somehow.
In the system.
Somehow I built a wall by I conserved energy. And I conserved my extensive variable.
So you
I did something. I did something. I did something on the system, and there is a wall such that the size of the system is the same and the energy of the system is the same.
okay, and then from SB to SA you just remove.
I just remove it, but in the middle I put this adiabatic boundary condition.
And the adiabatic, they won't exist on the first.
No, I don't need them.
Okay.
Okay.
How can you keep it?
Don't ask me how. I'm a theoretician, right? Theoretician. You don't ask Einstein how he got this question. So, but this is a thought experiment. Now, is it possible to do it in a lab? The answer is yes. Okay, so you can do the building process very, very slowly, and you can do the extraction process extremely fast.
And it be adiabatic.
Oh, yeah, almost adiabatic. Yes. Well, you can do it. So the question is, what kind of change or modification in the temperature I'm neglecting? I always neglect something. And my claim here is if I do it fast enough, I don't have to neglect a lot. You're right that in principle there is not such a thing as adiabatic boundary conditions. No. Right? So there is always some sort of a heat flow inside. But sometimes it's so slow and so small that I can simply neglect it.
But like you can push it out, you can put it in.
But I don't want to.
But then you can say in the same argument that
Okay.
SB is bigger than SA.
Oh, but if it's adiabatic, this is why, and I was listening to you, this is why I put an equal sign over here. Okay? You're absolutely right. This is SB is with constraint is smaller or equal to SA without constraint. Okay? You are absolutely right. I need an equality sign. Yes.
SA גדול מ-SB רק מהסיבה הגידול של הקיר באמצע?
Exactly. So the question is SA is greater than SB just because I introduced the internal constraint? And the answer is yes. And this is the principle of maximal entropy. The entropy is maximal with respect to what? With respect to any internal constraints. Okay? So if I have an equilibrium state and I have an entropy of this state and it can be defined, right? Entropy we defined so far only for equilibrium. Any constraints that I introduce into the system, this is what this principle tells us, will reduce the entropy. This is the general statement of maximal entropy. For any equilibrium system, the entropy is maximal. Maximal with respect to what? With respect to introducing internal constraints, internal modifications.
Yeah, but this is, you need to להניח.
You can ask in Hebrew.
אז צריך להניח שהדרך חזרה היא בתהליך הדיאבטי.
Yes, but I can do it. I can do it. Okay. This is this question of, can I do it fast enough in order to close the hole, right? Let's assume I can. Yes. A little bit louder, I barely can hear it. Oh, so we are talking here about a macroscopical system, so equilibrium defined by external variables, and it has to be global. For this specific energy and this specific extensive variables, there must be one. Yes, you're absolutely right. Okay? This is a very strong assumption because you can say, well, maybe there are several. And this principle tells us, no, there is only one. Okay? Any other questions? Yes.
אתה מקבל את האנרגיה ואת הפרמטרים החיצוניים רק ברגע שאתה עובר מ-S ל-SA, נכון?
No, all the way, so the question is what I do with energy and extensive variables. All the way when going from A to B, E kept constant and extensive variables are kept constant.
אוקיי,
This is important.
רק עוד דבר אחד קצר, אנחנו מגדירים אנטרופיה, קודש מספר מצבים, אני יכול להגדיר אנטרופיה באופן כללי, לא?
No, so the question, how do I define entropy? I don't know, I just said what is entropy, how I defined it. There is a function that is monotonically grows with energy. That's it. This function has a maximum. I told you that there is a function, and I told you that it has a maximum. I haven't described to you how it depends on different variables, but I just, out of thin air, took this principle. Okay? Exactly. Okay, are we fast enough? So how we can use this principle? How we can use this principle of maximal entropy? Okay. So let's assume I have two systems. Let's assume that I have two systems in a contact, and the energy of one system is E1, and the energy of a second system is A1 and A2. And they are in a contact. Okay? And I want to know something about what are going to be the values of E1 and E2. What I need to do? I need to maximize my entropy with respect to something. Okay? So the principle here of how I'm achieving different types of mathematical, thermodynamical laws and relations. Okay? I look on the system and I start to think, well, if I introduce some sort of a constraint to the system, I know that there should be a maximum of entropy. So anything that I do internally to the system should reduce entropy. Reduce, because I do something to the system. Okay? If I leave the system in equilibrium, the entropy is a maximum. Anything that I will do to the system will decrease the entropy. Okay?
Or equal.
If I do this adiabatically.
SP is not an equilibrium state?
Well, it is if I leave it over here.
Okay.
It is, but it has an internal constraint. Okay, so this is nice, but this is the maximum entropy. Now, this was a very nice question. And the question is, well, how entropy is defined, and entropy is growing or decreasing. Entropy is not a concept that we are used to work with, right? Or another concept that we really have an intuition about. What do we have intuition about? What we have been taught for 2 years, or even in high school. There is another quantity that is also ill-defined. We don't really understand it, but at least we're used to it. Energy, right? So energy. Entropy is maximal. What about energy? What we can say about energy? There is a principle of maximal entropy. Is there a principle about energy?
Minimal energy, maybe?
Yes or no? Okay, so let's see. So I do know that when I introduce internal variables, any questions? I'm here to answer questions. Okay. So we know that there is a maximum entropy. Now, maximum entropy I achieved when all the other variables, energy and my extensive variables, were kept constant. Okay. So when I'm asking about energy, what do I need to keep constant? I need to keep constant the extensive variables and the entropy. Entropy, I'm going to modify this internal parameter somehow. Okay, but I need to keep constant or everything else. And everything else, if I'm looking at energy, is also entropy. So what do we know so far? X is internal parameter. Okay. And we know that ds to the x of E equals 0. And we also know that the second derivative, d squared s dx squared, is, with respect to E, is smaller than 0. Okay, so this is our maximal principle. And x is our internal parameter. Now we are basically changing variables. Instead of looking on entropy, we're looking on energy. Beforehand energy constant, now entropy is constant, so we do know that S as a function of E of x is constant. So d of S in x equals 0, right? Because the differential of something which is constant is simply 0. So what do we have? That 0 is equals to ds to dE plus ds to dx x dx equals 0.
But how can we keep the entropy constant if the energy is changing?
Why not?
Because the entropy is a function of energy.
Well, I'm doing something else inside the system. What I'm changing? I'm changing the internal parameter, right? And I'm trying to look on this already mathematically, right? Because this maximal entropy is a variational principle. I vary something and I know that the response or this function should be maximal. I'm doing exactly the same thing with just some sort of a change of variables. Okay. Yes, the size of the wall or the amount of the holes inside the wall. Okay. No. So number of molecules is an extensive parameter which is global, right? Not something that I can change. Basically, when we are studying a little bit more about statistical mechanics, entropy is related to the number of states, and you have heard this. So when I'm building this wall, think about it. When I'm building any wall, beforehand, each particle can be in the hole of the chamber, right? I build a wall, and I restricted my particle over here, and it cannot longer penetrate to this side. So its energy, its entropy, has to decrease. Right? This is the microscopical intuition, right? We don't need this in thermodynamics because we're treating macroscopical quantities, and we don't know that there are molecules, right? But microscopically, what happens the moment I introduce constraints? The number of states of the system has to decrease, and the number of states is related to the entropy of the system. Okay? If you want to keep it in mind. All right. So what do we have here? So 0 equals to ds dx, dE ds dx. So we can obtain that dE to dx equals to ds to dx with E divided by ds to dE to x with a sign of minus. Okay. So what we want to define d, which is d to dx with constant s, it equals to what we have over here, ds to dx e divided by ds to d e x. We have a minus. Okay. And what is ds to dE with x?
dx.
This is, what is dE to ds? Temperature. So this is 1 over temperature. So we have minus T, right? ds to dx of E. What is ds to dx of E? 0. Okay, so we have this. We obtain that dE to dx with when s is constant, it equals to 0. So we know it's some sort of a critical point, right? Not critical. Maybe maximal, maybe minimal, I don't really know, but at least it equals 0. Okay? Now we want to say something more important, not just that it's a point, maybe maximum, maybe minimum. We want to say something more constructive, like with the case of entropy. So this is an extremum point. Extremum point. And we need to go to the next derivative, right? We need to go to d squared e to d x squared with respect to s, okay? And compute this derivative as well.
And extremum of what?
Extremum of e with respect to x, right? Because the derivative of e with respect to x is 0. So e with respect to x.
Why is it not an extremum of the entropy as well?
It is an extremum of entropy as well, because it's computed exactly the same point at equilibrium. But entropy is maximal. We don't really know what's energy. Okay? Yes. Over here. So I'm basically saying this was 0. Okay? And what I've done, it can be proved mathematically explicitly. But think about it, that I divided dE by this, both sides of this by dx, and then I divided everything by ds to d. Okay? It's good enough. It can be proved thoroughly, but this is enough. Okay? I basically divided this differential, but this differential and said this is a partial derivative. Okay, so what we have here, it is dx, d to dx of this function d that I have over here. Now, what it equals to? It equals to I'm changing variables over here. I have x and s, and I want to introduce some other variables, which is dB to dE, dE to dx. This is x, this is s, plus dd to dx of E, dx to dx. Oh, and I even don't need this term. Okay? Yes.
Why did we define that the entropy is a constant?
Because this is what I wanted to say. Remember, when I treated entropy, what was constant?
When I wanted the entropy, what was constant is the energy.
Energy. And now I'm treating energy, so I'm taking entropy constant.
So you can find the energy as it depends on constant.
Why
So
not?
we want the energy when the S is the maximum?
I don't know what about S. S now is a constant value.
Okay.
Okay? And I'm treating E as a function of some internal parameter.
So energy is now a function of S and other.
Look, first time S can be changed. Second time energy can be changed. How exactly I'm keeping entropy constant? It's a different question. Let's assume that I can. This is like a mathematical description, and let's assume that I can. Remember, what is theoretical physics is about? We start with some concepts, and then we apply a bunch of mathematical tricks on this concept. Okay. And as long as I don't do something crazy with my mathematics, it's okay. There is always this question: can I perform this in a lab? Right? And I don't really know. Okay. Well, definitely not by me, but because it's really, really, really hard to keep this value constant.
Okay, so why do we do a differential of S instead of E?
Because E, we want to, you will see in a second, okay? Yes.
Can you explain the S transition? Like some of the transitions I understand it's fine from a full derivative to partial derivative, but from here I don't understand the last part of the dot D. DE
plus DD dx. Right? This is correct? dx. Yes? Let's do this trick as I did it over here. Let's multiply everything by dx. Okay? Fine enough? But we need like a full board of derivations in order to prove that dd dx, when I do this, is actually dd to dx. But this is legit. Okay? But you start with this, you divide it by dx, and you're getting d to dd dx, dd dx, blah blah blah. Right? Yes.
D is do x.
It's only in Bar-Ilan we use this do.
But
I don't think that anywhere in this world nobody uses do. So I discovered that I arrived to the University of Chicago and I'm like, do to do to do to do. They were looking at me. What is do? But yes, do whatever to do dx. Yes.
No, D is dx keep as constant.
Yes.
And it's 0.
It is 0.
So why are we deriving it again?
You can have a function that the first derivative is 0, but the second derivative is positive, negative, 0, and sometimes complex.
What, are we putting some variable in it?
No? You have a function. You have a function.
That is 0.
Okay, let's do this like this. Do this like this. So f of x equals x squared. Okay, df to dx at x equals 0 equals to
So we are
0, right? This is 2x. This is equals 0. X equals 0.
So we are putting some variable in.
At what point we have computed it?
Yeah, okay.
This guy. Okay, right? And this guy we say that this is always satisfied. Always.
Always.
So, okay.
Yeah.
So it says that if the entropy, if the derivative of entropy,
It's not if, it is.
it is 0.
It is 0.
So it means that it doesn't depend in the internal parameter.
No, not exactly. So locally it is 0. But if I'm taking the second derivative, it's like this. Look on this example. df to dx equals 2x, and if x equals 0, it equals 0, right? What is the second derivative?
2.
2. So it's fine.
But
So it's a value.
But that's at a
You get
specific
value.
point.
I can get a value. The thing is that if the first derivative is 0, so locally it's 0. But I want to see what happens if I change it a little bit. A little bit. Right? So to the first, I can say, expand it in a Taylor series. Any function, if it's analytical, can be expandable in a Taylor series. So in the series, the first term is 0. But what about all the rest?
So D.
I want to continue. I want to finish this calculation. Sorry. I want to finish it and later we will talk. Okay, so we have this. Okay. Now, what do we still know? we have d to dE of x, and we know that this is 0. Look on this term. We proved that d, where is this? dE to dx, this term, okay, equals 0. Okay? So what we've got so far is that the second derivative of E with respect to S equals to the first derivative of D with respect to X and E. Which is d to dx minus ds to dx of E divided by ds to dE of x, right? And all of this is E. Okay, so nothing scary about this, right? Let's take the derivative. So what we have over here, we have the derivative of this guy, and then we have the derivative of that guy.
But the s to dx when E constant is not 0.
No, you have to take the derivative. The rule of derivatives. You first take the derivative and then you submit equals to 0, okay?
So it isn't a specific point.
Always, it's an equilibrium,
Okay.
right? Everything that we compute here is for equilibrium. So there are specific variables like s and the extensive variables that are kept constant.
Okay.
Right? Okay. So what we have over here, we have minus the second derivative of s with respect to x squared, thank you, divided by ds to dE of x, and we have plus ds with respect to dx, d square s dx dE divided by ds dE squared. I have a quotient. So I first take the derivative of this guy, and then I take a derivative of 1 over this guy. Think about our two functions. This is f of x, this is g of x. This is why, yes?
So this is a double equal
No, this is the derivative of this ds to dx. And this is why I have still minus over here.
מה יש שם מונה? אחד חלקי זה חסר.
D, where?
המונה כאן, המונה ש...
This?
זה השורה השנייה, השורה
This?
השנייה.
This?
כן, קצת שמאלה.
D to dx.
זה D קטן או שזה כאילו מהצורה של...
This is the dot, okay?
הצורה של הפילוסוף.
Yes, the dot. Okay, so what we know is 0. What is 0? In all of this calculation, everything becomes 0, and this is why I changed my variables. What is 0 in this guy? The right, right? ds to dx for a constant E has to be 0, right? As in an extremum. Okay? So what we got is that d squared E to dx squared at a constant s equals to minus d squared s to dx squared divided by ds to dE of x.
Do you want me to keep the energy constant?
Keep the energy constant. Keep the energy constant. What is ds to dE with x?
The temperature.
The temperature. We have minus t, d squared s, dx squared, constant E. So this is minus. Temperature must be positive. So this is smaller than 0. This is greater than 0. What about this? This is the second derivative of s with respect to the internal constraints when the energy kept constant. What is the principle for the entropy? It is maximal. So the second derivative is Negative. Negative. Okay, so we have plus, minus, and minus, and all of this is plus. Okay. And this proves what? Why we did all of this dancing in front of the board. The principle of minimal energy, you are absolutely right. The principle of minimal energy with respect to internal constraints.
If we assume minimal energy, will we get maximum entropy?
Yes, it works the other way around too. Okay? It is. But you have to assume something. You have to start with some, and this is the principle of minimal energy, the principle of maximal entropy. There are also other minimal and maximal principles, but you have to assume with one of them, and all the other just pop out. Okay. Yes?
Why couldn't we derive this from the equation we said earlier? We would define d as minus t and times the derivative of s.
Because everything went to zero. Everything went to zero over there. This was the first derivative and it went to zero.
But we just derived this again, so why?
What do you mean? This? No. So I don't really know.
Why couldn't we just derive d at that point where we had t already there?
Yes, but it was the first derivative of e. That equation was the first derivative, not the second.
Yeah, and we just did the second derivative, but we had t there already. We didn't need to do.
So you wanted to just to
variable change.
because the derivative of t with respect to all different quantities is also okay, right? Okay, so now, do we want, or no? You definitely don't want to, but it's exactly in the same fashion. We can derive the variational principles of all the generalized potentials. So this, in the same fashion as we did here with energy, right? We can do the same for enthalpy, enthalpy, the Gibbs free energy, free energy. What else do we have? And we have general Helmholtz, Helmholtz. All different names from the 19th century. And grand canonical potential. Grand canonical potential. For all of them, we have this variational or maximal with respect, no, minimal, I'm sorry. Minimal, they are exactly like the energy. Minimal with respect to internal constraints.
It worked with the same proof?
It exactly the same proof. So what we have done in the last 45 minutes or so, in 40 minutes, so we stated something, or he hypothesized something, right, about adiabatic process. Then we concluded that the energy must be maximal with respect to internal constraints. Okay. And then we danced a little bit with the mathematics and partial derivatives, okay, and we arrived that there is a principle of minimum energy, and there is all the other different generalized potentials that can be obtained from energy by Legendre transformation. So basically it's energy with respect to different variables. All of those are minimal. So if I want to look on the system and I want to observe when it's going to, what is the equilibrium state, I need to look, maybe somebody should provide me the energy. Okay? Somehow I'll get the function. I can obtain it from experiment. I can be given it as a function in an exam. And in order to find the equilibrium state, the proper thing to do is to find its minimal. Okay? And this is the only thing that matters for equilibrium. This is why they are so simple and so easy. We assume, as you said there, that there is one single equilibrium state, and this state is defined by the minimal of energy or the maximal of entropy. And that's it. This is why the theory of thermodynamics and the theory of statistical mechanics, okay, the equilibrium theory, is actually doable, and we can have a general theory because there is a very simple principle that lies behind everything that we are going to describe in this semester. There is some sort of minimal for each physical system. And in order to describe the behavior of the system, we need to work only around this minima. It doesn't matter how the system will reach this minima. The only thing that I need to describe for any given physical system at equilibrium is this minima, or the maxima of entropy if you really like entropy. I don't. Because I cannot understand its formula. Energy I'm used to, entropy less. And this is what we are going to try and achieve in this semester. We are going to try and achieve minima of energy, usually minima of energy, or minima of enthalpy, or minima of Gibbs free energy, or minima of Helmholtz, or minima of grand canonical potential. All the different energies or different descriptions satisfy or suitable for different problems. It's much more nicer to work with Gibbs free energy than with energy for specific systems. We will see how. But the only thing that we are going to do in thermodynamics or in statistical mechanics is to find this minima and describe the system around this minima. And that's it. Right? This is the story of this class. All right. So let's see a couple of examples of what can we do when we have this principle of minimal energy or principle of maximal entropy. Okay. Example number 1. I have two systems. Is E1, T1, and S1. And this is E2, T2, and S2. And they are connected, and I know that both two systems are in equilibrium. Okay. So I have two systems. This is the energy of the first one, the temperature of the first one, the entropy of the first one. This is the energy of the second one, the temperature of the second one, and the entropy of the second one. And I know that they are in equilibrium. Okay. Together. Right? They are connected. So whatever happened, happened. I'm looking on the system now, and I'm capable of measuring E1, T1, S1, and E2, T2, S2. Yes.
So how can I measure?
Somehow. This is system number 1. This is system number 2. I connected them, and they are connected. Well, I can prevent the particles from transporting from one to another. Somehow, for example, they connected such that the heat can flow from system 1 to system 2. Okay? Be specific. Let's allow heat to flow from one system to another, and they have reached some sort of an equilibrium. So the question is, how is T1 related to T2? So what can I do? How I can use my maximal energy, maximal entropy principle? Let's use maximal entropy principle. So I'm doing something to the system. Something. internally, okay, such that the total energy is not changing. So delta E is equals 0. So delta E1 plus delta E2 equals 0. I modified something internally. The energy can flow from one part to another in the form of heat or something, but the total energy is kept constant. And all the different other variables are kept constant as well. What do I know? That the total energy, entropy, I'm sorry, because it's an extensive quantity, so it's S1 plus S2, right? Always. The same works for energy. Why can I assume it? Because I assume that everything is macroscopical and the interaction over here is negligible. Okay. So what is the change of my entropy? This is ds1 to de1 delta E1 plus ds2 de2 delta E2. Okay. I perform some sort of modification. There is some sort of a change in the entropy. And this entropy, the change of the entropy, I can describe by writing the partial derivatives.
Because all the other things are constant?
Yeah, everything else is constant. Okay. So what is going over here? ds1 to d1 is 1 over t1, delta E1, plus ds2 to d2 is 1 over t2, delta E2. Delta E1 plus delta E2 equals 0. So I can simply say that this is 1 over T1 minus 1 over T2, and I'm getting delta E1 out of the equation. Now what do I know? I know that this delta S has to be
0 because around the maximum.
not 0. If it's around the derivative is 0, but the change itself is negative, right? Think about it. This is my function. This is S. This is X. The derivative is of 0. But if I've changed X a little bit to the left or to the right, delta S is negative. Okay? So all of this has to be negative. Okay. Now it has to be negative. This is the nice thing about this simple relation. It has to be negative no matter what I do. Right? I draw some red kishkush over here. Okay? Just and I said the entropy has to decrease. This is the nice thing about those maximal principles. No matter what I do, it has to decrease. So basically, delta E1 can be negative, positive, big, or large. It doesn't really matter. So this is a general variable, delta E1. It can be positive or negative. When this relation is satisfied, when delta E1 is anything, what do I get from this relation? This relation has to be satisfied for any delta E1. So this is for any delta E1. And I don't care if it's 0, negative, positive, or complex. So this, or complex it cannot be. It's energy.
Can you explain again why it's smaller than 0?
Because any change of the entropy is maximal. Any change has to decrease. Okay? That's it.
So when we do the red scribble.
Whatever. Yes.
It's not have to be 0 because they are.
Look what I'm getting over here. In order for this to be satisfied, basically 1 over T1 has to be O equal 1 over T2. Because it has to be 0. And because if I'm doing my shift small enough, the change is basically 0. Yes. Okay? So what I've got is that in equilibrium, any two systems in equilibrium have the same temperature.
Why
Why do you set it at 0?
Because it has to be satisfied for any delta E. Or what was your question?
Why it's equal 0?
Let's try and solve this. Can it be negative? Okay, T1 and T2 are constant. They are something. Okay, I'm changing this guy. I can make it bigger or smaller, positive or negative. This means that if this guy can be anything, then this guy also has to be anything else. But the temperatures are constant. And it's a maximal, so we did have this equality over here. Now usually thermodynamics works the other way around. So in the first class on thermodynamics, usually people start with this and say this is like a second law or the first law or part of the laws, part of the assumptions. But if we assume something about this function that we termed entropy and we said that it has to be maximal, everything that you have learned can be derived out of there. Questions? Yes?
Wait, but we said it is that the left side is smaller or equal 0. Why do we define it as 0?
Well, can you make it smaller than 0 and still satisfy this relation?
I have to make this entire thing smaller than 0.
Remember, T1 and T2 are constants.
Yes.
I do not modify them. They are constants. So can you, this is a constant value, constant, multiplied by something that can be anything. And it has to be always smaller than 0. Smaller or equal to 0.
Yeah, so it's impossible, so it has to be 0.
Exactly. Yes? This is part of my constraints. I look on them and I'm doing something internally such that the general energy does not change. If the general energy can change, there of course can be flow of heat from this system to the other system, the temperatures can change, and etc. etc. I'm assuming the energy is kept constant, and remember, my assumption for the entropy was when energy is constant and I'm modifying something, the entropy is at maximum. Yes?
Aren't we looking in the last equation here in the change in the temperature?
No, I don't want to change the temperature.
No, but you don't want to change the temperature. Therefore, delta E1 it is 0. It is the 0.
So there are two solutions to this guy. Either this guy is 0 or either that guy is 0. But delta E1 can be anything.
Why?
Well, I have no constraints because this kishkush can make it everything. Think about it. I haven't defined how exactly I'm making this, introducing this modification inside the system. The point is that the modification can be anything that you want, as long as the total energy is kept constant. Okay? Yes?
Can you repeat again, please, why delta E, delta E1 is supposed to be negative or equal in the last equation?
This?
Yeah.
So I'm saying the following. This is exact. Okay? This guy 1 over T1 minus 1 over T2 is constant. So I have a constant multiplied by a variable that can be anything, and it's smaller than 0. Smaller or equal to 0.
Why?
Because delta S is maximal. So any change that I introduce have to decrease S. Right? If you write a maximum, so anything that you do to the system, any shift will decrease the entropy. This is why delta S has to be negative. Or 0. Okay? Yes?
אז בעצם מה שאנחנו עושים פה, אנחנו מגדירים את S להיות פונקציה בהתאם לפרמטר T ו-E שאני מציב בתוכה, ואני מחפש מתי היא מקבלת מקסימום.
Yes? This is what we do. We find minimal and maximal of entropy or energy or Gibbs or enthalpy. This is what we are going to do. Right? Back to high school when you learn how to take derivatives.
ואז אנחנו בעצם מגדירים את הנתון בשלמה שתהיה הערך המקסימלי.
Yep. Okay. Example number 2. Okay. What is the other example? We have two temperatures, two systems. Okay. E1, S1, T1. E2, S2, T2. Now, they were not in equilibrium. Those two systems were not in equilibrium. Okay? Each of them had some specific temperature or an energy and etc. Now, I connect them and let those two systems reach equilibrium. Again, assumption. Okay? I assume that when I bring to contact two different systems, eventually, and allow them to exchange heat, allow them to exchange particles, allow them to exchange something, right? Eventually, those two systems will reach equilibrium. Okay. So, beforehand, so what is the difference between example number 1 and number 2? They were, previously were both in equilibrium already together. Now, they're not in equilibrium. I'm bringing them into contact and looking what happens to the system. So I'm starting and I'm bringing adiabatic boundary conditions on top of them. Right? I don't want any exchange adiabatic boundary conditions. I don't want to perform any exchange with the outside world. So the only contact is between this guy to that guy and equilibrization. Yep, of course. Well, nothing can be exchanged with the outside world. They can exchange something with each other. Okay, so I'm starting from some situation, okay, and I'm looking on what happens on delta S1 plus delta S2, which is delta S. Okay, so what this guy is going to be? Yes. So don't be fooled by that we have a maximal entropy principle. Maximal principle and entropy principle is when the system is in equilibrium already. Here the system is not in equilibrium, something is going on, and only afterwards it reaches equilibrium. And because I have this adiabatic boundary conditions, right, I know that this guy is greater than 0. It's a little bit confusing. Sometimes I'm saying, oh, delta S is smaller than 0. And sometimes I'm shouting out, delta S is greater than 0. It all depends if we're looking in an equilibrium state or reaching an equilibrium state. Two different perspectives. Okay, so we can do this thing again, right? We can have this delta S1 dE1, delta E1, delta E1, plus delta S2, delta E2, delta E2, and this is greater than 0. Again, no energy flow out of the system or into the system. So we have the same equation as over here. 1 over T1 minus 1 over T2 delta E1 greater than 0. Okay, so it's a little bit counterintuitive. In example 1 I have smaller than 0, in example number 2 I have greater than 0, but the two contexts are different. In equilibrium and reaching to equilibrium. If beforehand I modified my energy, I did something by hand, here I haven't done anything, just contacted them, and the system does something on its own. Okay? So this is the difference. Beforehand I did something, this time I just make a contact. So we have two cases. If T1 is greater than T2. So what happens if T1 is greater than T2? If T1 greater than T2, then 1 over T1 minus 1 over T2 is positive?
Negative.
Negative. Is negative, meaning that delta E1 is negative. Right? So what it means, the heat flows from
E1 to E2.
exactly from a hotter system to a colder system. Intuitive, right? So this is why usually you start with this, but you can obtain it from our maximum principle. Okay? And if T2 larger than T1, what we will obtain that delta E1 is positive. Okay? So this is simple, right? The heat flows from a hot system to a cool system, and not the other way around.
It's not a reversible process, so it can't be zero?
Yes. Usually, if most of the processes in physics are irreversible. Yes.
May I ask a question?
Yes. Sure.
The delta E1 from the most right one, the column, is the same as the delta with the triangle E1? Or
Yes.
Or the triangle delta is the total when
The triangle delta is you want to say as this?
Yes.
Okay, let's do this. It's here is an infinitesimal change of Q1.
So the triangle is also in the right one, the infinitesimal, right?
Yeah.
I'm sure it means the infinitesimal. Okay.
Any other questions? So we can get quite a lot. We can get quite a lot from these systems, right? Let's do example number 3. Let's do example number 3. It's out of equilibrium. Okay. Okay, so example number 3. Okay. Example number 3. Let's assume that I have two systems. In a contact. S1, V1.
למה פה חילקנו למקרים? בפעם קודמת לא חילקנו למקרים.
I will explain to you later. I really need to continue. Sorry. S2, V2, and N2. So two equations. Now they are again in equilibrium. Okay, so example number 1, everything was in equilibrium. Example number 2, this is an answer to your question. It has been not in equilibrium and it equilibrated during the process. Okay. Example number 3, everything is again in equilibrium. Okay. Two systems in a contact and they are in equilibrium. Now I can do something to the system, right? So the equilibrium is total equilibrium for the system. Those two systems are in equilibrium with each other. Okay? Now, I know that when I'm doing something to the system, for example, number 1, what I used the principle of maximal entropy. Here I'm using the principle of minimal energy. Right? So delta S1, I'm applying internal modification. Right? I'm applying internal modification, and I want to use the minimal energy principle. So delta S1 plus delta S2 equals 0. Delta V1 plus delta V2 equals 0. And delta N1 plus delta N2 equals 0. with the modification. So they were in equilibrium. There was S2, V2, N2, S1, V1, N1. This is an equilibrium state. I applied an internal constraint, and there are some modifications in the entropies, in the volumes, and in the number of particles, or number of moles. So what is delta E? So what is delta E? I can use, remember the equation, dE equals PdS minus PdV plus mu dN. So what is delta E? It's delta E1 plus E2, right? The energy is extensive. I will start with saying, well, no matter what I do, the minimal energy principle tells me that this guy has to be positive. Okay. This delta is a linear operator. It's simply the change in E1 plus the change in E2. Delta E1, delta E2. It equals to, according to this equation, T1 ds1 minus P1 dV1 plus mu1 dN1 minus T2 ds2 minus plus P2 dV2 minus mu2 dN2.
Why is the second one in minus?
Plus. My bad, sorry. Now they're going to be with the minus. So T1 ds1, okay, plus P1 dV1 minus, I'm sorry, dV1 plus mu1 dN1, okay, minus T1 ds1. So what I have done, basically here I'm saying delta S1 equals minus delta S2. Delta V1 equals minus delta V2. And delta N1 equals minus delta N2. Okay? So I have just performed this change of variables over here. Delta S1 plus P, this is 2, P2 dV1 minus mu2 dN1. So in total I'm getting T1 minus T2 dV1 ds minus P1 minus P2 dV1 plus mu1 minus mu2 dN1. And all of this is greater than 0. Now, my internal modifications are unconstrained. I can make delta S1 positive or negative. I can make delta V1 positive or negative. I can make delta N1 positive or negative. Okay, so if we look on this sum is greater than 0, greater or equals to 0. This can be whatever I want, this can be whatever I want, and this can be whatever I want. When all of this inequality or equality is satisfied, okay, only when T1 equals T2. But we already seen that, right? Two systems in equilibrium, the temperatures has to be exactly the same. But this goes on. P1 equals to P2. Mu1 equals to mu2. And this is a general principle. Yes?
If I added some internal modification, shouldn't the entropy decrease?
But I'm not looking on the entropy.
Yeah, but
Entropy will decrease if I'm keeping my energy constant. I'm not keeping my energy constant. You see, I can keep different kinds of things constant. Sometimes I decide to keep energy constant. And sometimes I decide to keep the total entropy constant.
but it's like earlier you added the wall and the entropy decreased. Why is not?
Only for a specific system, when I kept my total energy constant. Okay? So here, what I was keeping constant, the entropy was kept constant. The volume was kept constant, and the number of particles was kept constant. Yeah. Okay. So our general principle is as follows. In equilibrium, between any two systems, all the intensive generalized forces are equal. So in my equilibrium, the pressure has to be of 2 systems, 3 systems, 4 systems, it doesn't really matter. The pressure has to be constant. The temperature has to be constant. Any generalized force that I can imagine, and here the chemical potential is a generalized force, it has to be constant. Okay? Extensive variables can be whatever they want. Intensive forces has to be exactly the same all over the system. Okay? There is no flow of anything. Everything is exactly the same. If there was a difference in the pressures, one system will push the other one outside. Because the pressures are exactly the same, this is what makes the system an equilibrium system. And in the same fashion as we have done it over here, we can, if you remember, we had f dot dx, right? This is generalized forces, this is generalized extensive coordinates, intensive, extensive. All of those f's have to be exactly the same all over the system. Because, right? Because what I can do, I can say the following. I have only one system, and let's imagine that, okay, I'm separating it into 2 systems. This is system A, and this is system B, like Venn diagrams. Okay? It doesn't matter, as long as A is macroscopical and B is macroscopical, I can say that the pressure inside this system has to be exactly the same as the pressure of this system. And the chemical potential of this system has to be exactly the same chemical potential of that system. And the temperatures. Why? Because there is a very strong constraint. The systems are in equilibrium. It's extremely strong statement. Questions? Yes?
I can say that the 2 systems are in equilibrium and the total energy is minimal, but I can't say that to each system on their own, right?
Exactly. Exactly. You're absolutely right. You're absolutely right. This statement is about the whole system, not some sort of specific subsystems. It is a stronger statement, and it does not always hold what you say.
Can I define temperature to the whole system?
Yes.
Okay.
And it's going to be equal to?
The whole entropy? Yeah.
Exactly. Okay, so one last thing that we have to do. What? It has to be. Okay, so the question is, what we have obtained over here, the question is why energy has to be smaller or larger. So this is the principle of minimal energy. This is what we proved, right? Maximal entropy, minimal energy. Okay. So this has to be satisfied because this is one of our assumptions about how the world works. This is the variational principle. Yes, of course, but I did something internally. So no. So what the maximal minimal energy principle says. You have a system. It doesn't matter of how many subsystems it's composed. and you do something internally to the system, the energy is going to go up. Yes, internally. When you do something internally to the system, the energy goes up. No matter what you do. No matter how much you try and how you try, the energy has to go up. This is the principle. Okay, so last thing for today, and I will take 10 minutes out of you. No questions. Next example. I'm late and you had asked me a lot today. A lot. Who likes properties of the functions? Concave, convex. Okay. Concave vs convex. תמורה וכאורה. Oh, we'll answer this question. What is convex and what is concave? And the principle in Hebrew, whatever you think it is, it's the opposite. Okay? This is the principle. This is how I remember it. If you think that whatever you think about kamu or ka'u, it's the opposite of what you think. Okay, so why do I, wait. Why do I need this, guys? Okay, so remember the following statement. We know if this is entropy and this is energy, okay? We know that entropy is a monotonically growing function of energy, right? So it can be something like this, it can be something like this, and it can be something like this. Okay? Our principle we haven't said how exactly it is growing, right? The second law of thermodynamics, or the outcome of the second law of thermodynamics, basically said to us that entropy has to grow with energy. But there are different types of growth in mathematics, right? Remember, all of thermodynamics is the properties of analytical functions or non-analytical functions, right? So there are monotonically growing functions, but there is a big and crucial distinction between concave function, convex function, and a concave function. Concave function. Okay, so let's make the distinction between concave and convex.
No one knows.
Who knows? As I told you, whatever you think is the opposite. But in English it's actually fine. Okay, so if you in English, this looks like a cave. So this is concave. Okay? Now this looks, I don't know how, but this is convex. Okay? Convex. And we do this in Hebrew. It's the opposite. Okay? So we plot this. It looks like a ball, right? It looks like a ball. So we think it's a keura, right? So it's a ball. The camel. Okay, this is why I've written it on the page. Okay? So this is camel. No. Camel. No. This is why I have written it over here. I had a big fight this Saturday with my father-in-law about this. Please, this is camel, and that's it. Okay, I checked in Wikipedia. So in English it is perfectly fine. In Hebrew, it looks like a ball, so you think Kiara, but this is the other way around. Okay? Okay, Kramu. Okay, and so convex function is Kamo.
Yeah.
Kamo. And a concave function is ka'u. Okay? This is how they are defined in Hebrew. It's the opposite of whatever you think it is. No matter what you think. Alright, so why it is important and basically why I'm telling you about this, except that we learned this in first year and usually never remembered why people talk about it. And the following is as follows. Let's assume that our function is convex. Okay? Okay, so this is S, this is U. So this is my U. This is U minus delta U. And this is U plus delta U. Delta U. This is convex. This is convex. Okay. It cannot be negative. Sorry. It has to be, it has to grow, right? And I plotted you something which is not physical. So this is this. Okay? Yes?
Is temperature is the non-negativity of temperature consequence of one of the three laws of thermodynamics?
It is because S is a growing function of U. Yes. Based on second law. Yeah. This is the second law.
If E decreases, can't S...
So it has to satisfy this law no matter what. Otherwise it's not equilibrium. Anything can happen outside of equilibrium. In equilibrium it has to be satisfied. Okay? Alright, so this guy is S of U minus delta U. This guy here. Sorry, Bob?
U is the energy?
U is the energy. U is the energy. S of U. And this is S of U plus delta. No. So convex means is that we have a value, okay, and we plot a chord from one point to another, okay, and the function or any value of the functions for any values of U between the left hand side of the chord and the right hand side of the chord is always below this chord. Okay, so it basically says that S of U plus delta U, okay, plus S of U minus delta U divided by 2 always greater or equals to S of U. This is the definition of a convex function. Convex function. So the average of those 2 points, it's always above the average of those 2 points. Okay. So let's assume that entropy could be a convex function. Entropy could be a convex function. What will happen if entropy, what happens if entropy is a convex function of energy?
So maybe in the function we can see that it's not convex, it's concave.
Where it's concave?
If we go down in the
Oh, but at least here it can be convex.
yes.
Okay. You want me to continue with this in this following way? Okay. So it's convex everywhere. Okay? But it's even locally it cannot be convex. Okay. So why it's important? Let's assume that we have two systems, and they're exactly in equilibrium. Everything is in equilibrium. We have S, U, V, and N. We have S, U, V, and N. Okay. Now we do something to those systems. And we have here on the left-hand side S, U, minus delta U, V, and N. And we have here S, U, plus delta U, and V and N. So I prepared those two systems. Okay. I prepared those two systems. And they are in equilibrium, but they are somehow separated. Everything is exactly the same, and the entropy is also the same. Okay? And the entropy is also the same. Now, according to this, what will happen if I let this system evolve adiabatically? What will if I start from this system, which I have two systems and I set them in equilibrium, and they have exactly the same internal properties, and they have exactly the same external variables, and they have all the generalized forces are exactly equal. Everything is equal in those two systems. And I let them be.
Remain the same.
Oh, adiabatically. What will happen? According to this principle, if entropy is a convex function of energy, what will happen? The entropy here is 2S of U. The entropy here is S U plus delta U plus entropy of U minus delta U. What is bigger? This guy is bigger. Okay? So the system would like to evolve into this system, right? The entropy wants to grow. I do not prevent it. It's exactly the same system. There is no separating wall. Something have to change inside the system such that the entropy will grow. And what is going to change? The energy from this left-hand side will flow to the energy on the right-hand side. But what happens in equilibrium? No flows, right? Nothing flows. The temperature is exactly the same. The pressure is the same. Nothing flows. No flows, no currents. This is the description of equilibrium. And here, the energy is flowing. The heat is flowing from the left-hand side to the right-hand side. But the temperatures are exactly the same. Why can't heat flow? And the answer is, it can't. Why it can't? Because entropy cannot be a convex function of the energy. Okay? It has to be a concave function of the energy. Okay? It has to be. And this is the proof, because if entropy was a convex function of the energy, we would allow a flow of heat from one part of the system to another. Two systems in equilibrium, exactly the same temperatures, and still there is a flow of heat. We don't see such things in nature, okay? And this is why we don't see convex entropies, right?
There is no interaction between these two systems?
No, the same system. I just assume that they are exactly the same. I connected them. The heat can flow. I allow the heat to flow, but it can't. Okay, so I will just write the final. There is a very nice outcome out of this concavity of the entropy. Okay? And I won't prove it to you today. I will prove it to you next week. Okay. But the theorem that is based on concavity of entropy is as follows. Don't worry, I will prove it to you next week, if you're worried. Okay, so if I have phi, okay, if I have phi, and phi is the energy. Assume I have energy, and the energy is T ds minus P dV plus mu dn. So the theorem tells us the following thing: dt to d ds to dt greater than 0. D minus P to dV greater or equals to 0. D mu pdn greater or equals to 0.
Isn't it supposed to be dV?
D what? No. Ah, this guy, yes. So what we obtain out of this is that we not only know that in equilibrium that the stability criteria, that the temperatures and the pressures and the chemical potentials has to be constant. We also know that there are positive derivatives of the conjugate variables with the real variables, right? So this variable with respect to its, so this is a conjugate variable with respect to a real variable, the derivative is 0. The same goes for this guy, and the same goes for that guy. And I will explain to you exactly how we approach it and what we find next week. Yom Shlishi and Shul. There is no class on Tuesday. Go and vote for someone.